Hello, everyone. This is the supplementary medium aiming for the review of quantum mechanics. Okay, so in this supplementary, I'm going to divide these materials into 5 parts. So this is the first part, which is about the Schrödinger equations. Okay, so I'm going to introduce to you the basics of the Schrödinger equations, and this is the fundamental approach to the quantum mechanics. So in this part, I'm going to show you the origin of Schrödinger equation, and then I'm going to show you the time-independent and the time-dependent Schrödinger equation. And following, I'm going to give you the physical interpretation and the implications of the results of the Schrödinger equations. Okay, so the origin of Schrödinger equations. As we know that there are several observable properties of a particle. So these are the key observable properties of particles, that including the mass of the particle. We use the m to represent it, or the positions. Of course, we can measure the positions in the x direction and y directions or z directions or the coordinates. And we can also measure the momentums in 3 coordinates in terms of the px, py, and pz. And of course, we can also obtain and observe or measure the energy of the particle. We use the E to represent it. Based on the classical wave equations and the Broglie matter wave concept, Schrödinger proposed that the wave equation, if we can form or formulate a wave equation, this wave equation must be valid and applicable in describing the matter wave-like particle. Okay, so based on this, the Broglie matter wave particles, it is a particle, but it behaves like a wave. So we should be able to write down the wave equations that must be valid and applicable to describe the matter wave-like particle, and regardless their specific energy and the moment or the momentum. So since the particle now can be regarded as a wave, we expect the solution to the wave equations must have the uh, familiar form with the wave functions. So these wave functions uh, is expressed in terms of the space and the time. So now we just here for the simplicity, we just assume the one-dimensional case that is in the x directions. So these wave functions uh, depends on the spatial dimensions x, and also depends on the time domain, okay, t. So these wave functions can be expressed as a is the amplitude of this wave function times exponential j kx minus omega t. So k is the wave number of this wave. X, of course, is the position in the x directions. And the t, of course, is the time. And here, omega is the angular frequency of these wave functions. And we also uh, uh, know that the wave equations contains appropriate the derivatives of wave functions, these 5 with respect to the coordinates x and the time. Okay, so these wave functions uh, must have appropriate derivatives with x, okay, for the first derivatives and the second derivative, okay, in order to obtain like the, for example, the velocity and the accelerations. And also, we must have this time, these wave functions to be able to have its derivatives with respect to the time, d phi over dt. We should be able to find these derivatives with appropriate values. And also, the wave equations must be valid independent of the specific energy and the momentum, which means that the particle should have a specific energy and the momentum. And from the classical physics, we know that the total energy of a particle can be expressed as this total energy, E, can be expressed as the summation of the kinetic energy, which is can be expressed as p squared divided by 2m. So this p is the momentum, the m is the mass of the particle, and the potential energy V. Okay, potential energy V. So this we denoted as equation 2. Previous one, these wave functions, solutions of the wave functions, we denoted as equation 1. Since we know that we have to fulfill that we can find appropriate derivatives of the phi, so we just take the first derivative with respect to the time, d phi over dt. Okay, since phi equals to this one, so d phi over dt give us the solution, that is minus j times a times omega exponential j kx minus omega t. Okay, so if you look at this a times exponential j times kx minus omega t, it returns to the wave function itself. So we take the first derivative with respect to the time, give us the wave function itself, but also we multiply this minus j times omega. Okay, so it is in proportional to the omega. So it is in proportional to the omega if we multiply with the h bar in front of it. This represents the energy. Okay, so the phi over dt implies the concept of energy. On the other hand, if we take second derivative with respect to the coordinates, so that is the square phi over the x squared, give us the minus a k squared times exponential j kx minus omega t. So again, you can see a times exponential j kx minus omega t is the wave function itself. Okay, and it multiplies with the k squared in front of it, which means that this one is in proportional. This second derivative with respect to the coordinates is proportional to the k squared. If we multiply h bar in front of it, that is h bar k squared. Okay, so h bar k, based on the Broglie matter wave concept, h bar k is the momentum of the particle. So second derivative with respect to the coordinates actually implies the square of the momentum. Therefore, we can set the wave equations as this one. d phi over dt is the energy, and this energy equals to the kinetic energy and the potential energy. The energy, okay, the energy is proportional to the first derivative of the wave function with respect to the time, and equals to the kinetic energy. Okay, kinetic energy actually equals to the square of the momentum divided by the 2m. Okay, so square of the momentum actually is in proportional to the second derivative of the wave function with respect to coordinates. Therefore, we assign a constant in front of this second derivative, and plus v times v represents the potential energy times phi. Therefore, if you compare, if you reorganize this equation 1, 2, 3, and compare with this classical energy expression, we are able to get the AB constant, and the AB constant can be determined in the following page. So substitute 1 and the 2 equations into equation 3. We can obtain the coefficient A now equals to J times H bar divided by 2m. B now equals to minus J divided by H bar. Okay, so we substitute this A and B back to this equation 3. Give us the equations. Okay, this equation is J times H bar times d phi over dt equals to minus H bar squared divided by 2m. D squared phi over dx squared plus v phi. So we call this one because it is only depends on valid in one dimension. So this is the one-dimensional time-dependent Schrödinger equations. Okay, so we can see that this, if you are going to solve these equations has dependence on time and the space. Okay, so this is called the time-dependent Schrödinger equations. If you want to extend from one dimension to three dimensions, so the Schrödinger equations now become J(h bar d phi over dt equals to minus h bar squared divided by 2m. This is Laplacian operators, Laplacian phi plus v phi. Okay, so this equations is the three-dimensional format of time-dependent Schrödinger equations. And because we know that the wave functions has a spatial dependence and a time dependence, therefore we are able to split the wave functions into the spatial dependent part functions and the time dependent functions. Okay, so spatial dependent functions we call it as this phi, and the time dependent parts we call it as x. Okay, so we substitute this one. Okay, we now can split the wave functions into spatial dependence and the time dependent. So we first take a look at the left hand side of the Schrödinger equations. We take the first derivative with time to the wave functions. Okay, so that is J(h bar). We take this part with respect to the time for the first derivative. Okay, so this should be equals to E times phi. Okay, this should be equals to E times phi. So this phi as a function of x and t now can be expressed as phi as a function of x times x as a function of t. So this one, because this one has nothing to do with the time, okay, so we move this out of this derivative and cancel both sides of these equations. Okay, so the remaining part is the xt divided by dt. So we move this one to the right hand side of the equations. It equals to minus j divided by h bar times e. Okay, since this one has been cancelled out, the remaining part is the x as a function of t. Okay, so this one is the first order differential equations, and I suppose you all know that the solution of this xt is exponential minus j times e divided by h bar times t. So it's a exponential functions. Okay, it's a exponential functions, and we know that e equals to h bar omega. So divided by h bar, now we obtain exponential minus j omega t. So xt is a time-dependent functions. It just has the form or just has the format that is exponential minus j omega t, which is just exactly the part, this part, okay, which is just exactly this time-dependent part. Okay, now we know that we can just separate the wave functions into the spatial dependence and the time dependent. Okay, since this time dependent equals to exponential j omega minus j omega t, so this time dependent parts can be eliminated, or we can write down this as this one times phi times xt, that equals to e times phi times xt, or we can use this jh bar d phi x dt, and since exponential, this xt is exponential minus j omega t, so this exponential j omega t can be eliminated on both sides and leaves this time independent part, only spatial dependent parts, the Schrödinger equations. Okay, so this is called the time independent Schrödinger equations. Okay, or you can move this one into here and use h instead of h bar, and that becomes this Laplacian phi plus a pi squared times m divided by h squared times e minus v times phi equals to 0. As we know that in the classical mechanics, a particle's total energy E can be expressed as 1 over 2m times momentum squared, okay? That is px squared plus py squared plus pz squared plus the potential energy V as a function of R, and it can be also time dependent T. Okay, so this E now can be expressed as this is the spatial and time dependent momentum plus spatial and time dependent V. We call this one as the Hamiltonian, as the total energy of a system. Okay, so this Hamiltonian H represents the total energy of the particle in this system, equals to 1 over px squared plus py squared plus pz squared divided by 2m plus v plus potential energy. Okay, therefore the Schrödinger equations can be written in the Hamiltonian form or the operator form. So we call this H as an operator. Therefore, the Schrödinger equations now give us JH bar times d phi over dt. Okay, of course, this wave functions is spatial and temperature dependent, equals to H times phi times this wave functions, where this H Hamiltonian is expressed as minus H bar squared divided by 2m, Laplacian plus V. Okay, so we call this H as a Hamiltonian operator. If we compare to the classical mechanics expressions with the wave functions, this is the classical mechanism. Just tell us E equals to P squared divided by 2m plus V. So in the classical physics, we are able to detect energy. We are able to detect the square of the momentum. We are able to give this system a potential energy. We are able to observe the exact position of x and y and z, and also we are able to determine the mass of this particle. Okay, but in terms of the quantum mechanics, things becomes very similar but a little bit complicated. So in terms of the energy, we express it as a JH bar. We take the first derivative of the wave functions with respect to the time. Okay, in the Hamiltonian part, we have minus H bar squared Laplacian divided by 2m plus V. Okay, plus V. Therefore, in the quantum mechanics, how can we evaluate the energy? We use this one, okay, JH bar, d phi over dt. So if we are going to evaluate or obtain energy, we have to use the operator. We use this operator acting on the wave functions, then gives us the value of energy. Similarly, if we are going to observe the momentum square, we can use this minus H bar squared times Laplacian. We acting on the wave functions. This gives us the square of the momentum. Okay, and the V is the potential functions. Okay, and the X, Y, and Z, and M is the mass of the particle. So this V, X, Y, and Z can also be operators. So Schrödinger proposed and defined the energy operators. Okay, as I mentioned in the previous slide, energy operators can be expressed as JH bar. Okay, d phi over dt. So the momentum operators, because we know that in the x directions, px squared. So that is minus h bar squared Laplacians in the x directions. So px can be expressed as h bar divided by j d phi over dx. Or you can Or you can write it down as minus JH d phi over dx. Okay, so this one can be also expressed as minus JH bar d phi over dy, and this one is expressed as minus JH bar d phi over dz. Okay, so with these definitions, Schrödinger equations in the operator form now becomes E phi equals to H phi. So if we consider this as an like a matrix, so H is n times n matrix. H can be regarded as an n by n matrix. Okay, n by n matrix. If you want to obtain this n by n matrix, we are able to calculate its eigenvectors phi. Okay, eigenvectors phi, and will give us the eigenenergy or eigenvalues lambda I times vi. Okay, so this one can be analogy to the linear algebra, which once we have these Hamiltonians, we are able to solve the eigenfunctions, and each eigenfunctions will correspond to a specific eigenvalue. This eigenvalue, of course, is the energy of the operator, this H Hamiltonian. And this eigenvalue, each specific values corresponding to the specific wave functions. Okay, specific wave functions. Okay, now let's turn to the time independent and the time-dependent Schrödinger equations. And we already know that the solutions of the Schrödinger equations can be separated into spatial-dependent and the time-dependent part. So substitute this into the Schrödinger equations. We have the this one, because we know that this the left-hand side of the Schrödinger equations is JH bar d phi xt divided by dt equals to E phi xt, E phi xt, and we now separate these two functions. Now we are able to get this x as a function of t equals to exponential minus j omega t. This is because omega or energy equals to omega times h bar. Okay, since we are able to eliminate the time-dependent part, now the spatial-dependent part gives us minus h bar square divided by 2m phi. Okay, we remove this phi over here, and the square phi divided by the x square plus v equals to e, or we can use this one to represent the time-independent Schrödinger equations. That is minus h bar square divided by 2m Laplacian plus v times phi equals to e phi. Okay, so this one is called the time-independent Schrödinger equations. You can also move this one into here and move this one into here, and then we get this Laplacian phi equals to 2m divided by h bar squared times e minus v times phi equals to 0. Or you can expand this h bar equals to 2 pi times h. Okay, and then you can obtain Laplacian phi plus a pi squared times m divided by h squared times e minus v times phi equals to 0. Or we can move this one into here and get h bar squared divided by 2m times Laplacian phi plus e minus v times phi equals to 0. No matter you use which equations, okay, once v is known, which means that the Hamiltonian is known, and then this is just identical to solve the eigenvalue problems. That once v is known, then we are able to get all allowed wave functions with corresponding eigenvalues, that is eigenenergies, E. Okay, and then we can solve all the solutions in this system. Okay, just as this example. So this one we use the simple atom as an example. Okay, simple atom as an example because in the single atoms, the potential energy is provided by the Coulomb interactions or Coulomb attractions between electrons and the nucleus, which carries the positive charge, and electrons carry the negative charge. So the potential energy has the form, okay, that is 1 over r, okay, the distance between nucleus and the electrons. Okay, so once we determine the potential energy, we are able to solve the wave functions phi1, phi2, and phi3, so on and so forth. And each wave functions will have its own eigenenergy, E1 and E2 and E3. So the the footnotes or 1 over here actually represents the fundamental solutions or the fundamental mode of this system, okay, of this system. And one thing you should know, this is very important, that although the Schrödinger equations looks pretty simple, okay, and as we described here, that once you know the potential energy, we are able to calculate all allowed wave functions and their corresponding eigenenergy E. But as a matter of fact, that only very few potential energy system allow us to solve the problems analytically. Okay, and they are listed in the following figures. There are only 4 I can show you right now. But of course, there are some few other systems, but not many. Okay, but not many. So first one is the infinite and the finite square quantum well. Okay, you should know this previously, that in the quantum well, the energy on the wave functions are quantized inside the quantum well. Okay, so the fundamental mode is phi1, and then the higher order modes comes with phi2 and phi3 with the higher energy. Okay, and the energy separations will be depends on the principal quantum numbers of these quantized states. Okay, so this one, square quantum well with finite and infinite potential barrier, will allow us to solve the wave functions and the eigenenergies analytically. And following is the simple atoms, okay? Only limited to the simple atoms like the hydrogen or the helium. Once the atoms is has a higher atomic numbers, and there will be many more than 2 electrons. Okay, more than 2 electrons. Things will get complicated. Okay, things will get complicated. And the other one is periodic atoms, like in the crystal structures. Okay, so in the periodical atoms, the wave function, the potential energies takes this form. Vx equals to Vx plus A. A is a periodicity or the lattice constant, which means that when we translate the positions, every distance A, the potential energies will repeat itself. Okay, will repeat itself. So this periodic atomic system will be derived in the lecture in chapter 2. So I'm not going to cover these derivations in this supplementary. And the final one is harmonic oscillators. Okay, so harmonic oscillators, just like the spring, so it oscillates using a spring, and when we press it or we extend it, the spring will start to oscillate back and forth. Okay, and that potential energy system has a function of the x squared dependence. Depends on the square of the position. Okay, so this energy is proportional to the position square. Okay, this one V is in proportional to 1 over R. So this V equals to 0 within the well and the infinite or finite energy in the barrier. Okay, so once the potential energy is in proportional to the x squared, we call it as a harmonic oscillators. Okay, in the harmonic oscillators or the parabolic well, the systems will quantize with equally spaced energy separations. This is a very interesting. This is a very interesting, and we will introduce these harmonic oscillators later in the later part. So this is amazing that only very few examples or very few potential energies can be solved analytically. So probably you will ask, uh, uh, if there's only very limited potential energies can be solved analytically, what other potential energies? How can we calculate that? Okay, so in that case, we probably have to use the so-called first principle or use the computer numerical methods to calculate the solutions of these Hamiltonian systems. Okay, so that turns the Schrödinger equations very difficult to solve, and it relies on the more advanced computational power to solve these problems. So, in the following, once we know the origin of the Schrödinger equations, now I'm going to give you some interpretations and the implications of the Schrödinger equations. And when the Schrödinger proposed the Schrödinger equations, he actually did not exactly know the physical meanings of these equations. Okay, but he only know that these equations can explain the atomic spectrum very well. But these equations cannot explain the photoelectric effect. Okay, as you may know that the photoelectric effect has been explained by Einstein. Okay, by Einstein, also applied the quantum mechanics. And these Schrödinger equations cannot also fit the Planck's formula. And as all you know that the Planck's formula, they tried to derive the expressions for the black body radiations, and only the Planck, he proposed this E equals to h bar omega. Okay, and then he can fit the Planck's formula. Okay, so Schrödinger equations can only explain the atomic spectrum well. And as to the physical meanings, he actually don't exactly know. Not until the Max Born, okay, in 1926, he tries to interpret what is the wave functions. So he regarded the wave functions as the probability amplitude of the particle, not limited to the electrons, at a particular position in time. Because we know that wave functions has to do or is the functions of the positions and the time. Okay, so he say that wave functions actually is the probability amplitude. Probability amplitude. So once we get the absolute values of this probability of these wave functions, then square of it, or you can express it as this one. This equals to phi complex conjugate times phi, and this has a physical meaning. The physical meaning of this phi squared actually is the probability density of the presence of the associated particle. Okay, so wave functions wave function square actually represents the probability to find the electrons at the particular positions in time. Okay, so this one actually against the picture or the concept that proposed by the Bohr. The Bohr proposed that the electrons move around the nucleus like the planets move around the sun, okay, like the Earth move around the sun, okay. So it has a fixed orbital. It has a fixed orbital. But once we interpret the wave functions as a probability density, now the orbit is not a correct pictures of the electron movements. Instead, the atomic pictures now becomes like the cloud of electrons. Okay, so you cannot specifically say the exact positions of the electrons, but you can say that the probability to find electrons at the specific positions. So that is the total difference in comparison to the classic physics. In the classical physics, we are able to tell the exact positions of the particle at the specific time. Okay, but the Max Born tried to interpret the wave functions as the probability density. Okay, so once it is a probability density, now the electrons is not a fixed point. Instead, it is becomes like the probability cloud around the atomic surface or outside the nucleus So you can draw an probability density as a function of the radius. Okay, you will find that at the center of the atoms, the probability to find the electrons is 0. That is because at the center there's a nucleus. Okay, but away from the nucleus, we are able to determine the maximum probability we can find the electrons over here. Okay, but that is just the probability. We're still not able to deterministic to determine at the specific time we can 100% make sure that the electrons locates over there. Okay, so this is the first interpretations by the Max Born that the wave functions square actually represents the probability density of the particle. Okay, so in the following, I'm going to give you 5 characteristics of the Schrödinger equations. First one is the probability density. Suppose this phi is a complex functions of a particle. And of course, we know that wave functions equals to a times exponential jkx minus omega t. So phi can be a complex, okay? Phi can be a complex function. Then we use the complex conjugate times phi now equals to phi absolute value squared. Now this one becomes the real quantities, okay? So this one is the real quantities that can be measured, that can be detected. So phi squared has a functional dependence, okay, as the previous peak. And then we know that phi complex conjugate times phi dx equals to phi absolute values phi squared dx. So if we integrate these functions from position A to B, okay, this should be a constant. Okay, this should be a constant because the electrons or the particles we can observe is a real quantity. Okay, so in 3-dimensional case, suppose there's a hydrogen atoms. At the center we have a nucleus. Okay, and around the nucleus we have electrons. Because it is a hydrogen atoms, so the electrons numbers is 1. Okay, electron numbers is 1. So we can normalize these wave functions probability, normalized in terms of the space and to 1. So which means that the probability to find the electrons is 100%. Okay, 100%, because there's only 1 electrons. Okay, because there's only 1 electrons. And this expression, okay, is the integration expressions. Sometimes we will use these direct notations. These direct notations, Bragg, this one is called the bra here. This one represents the cat, okay, represents the cat. So this cat actually is the wave functions itself. Okay, it's the wave function itself. This bra actually is the complex conjugate of the wave function. This one actually is the complex conjugate of the wave function. Okay, and this one is the wave function itself. So when we write down this phi over phi actually represents an integrations. Okay, that is complex conjugate phi times phi and integrate over the whole space. Okay, integrate over the whole space. This direct notation, these direct notations can be very, very helpful in the following derivations. Okay, so first one, we know that the probability density can be expressed as the phi complex conjugate times phi, or we use these direct notations to represent its integrations. And the second one, this is also a very important characteristic of these wave functions in the Schrödinger equations, is these wave functions themselves, they follow the orthogonality characteristics. What is orthogonality? We should all know that, for example, in the Cartesian coordinates, we have three coordinates, E1, E2, E3, or X, Y, and Z. And we know that they are mutually orthogonal. So what does it mean? They are mutually orthogonal, which means that when they use the dot product, okay, dot product, EI dot EJ equals to delta IJ. So what does it mean? It means that this delta IJ will have only two values, either 1 or 0. Okay, so when this equals to 1, only when I equals to j. When it equals to 0, that is I doesn't equals to j. Okay, I doesn't equals to j. So these unit vectors form a complete orthogonal set. Okay, complete orthogonal set of these wave functions, So similarly, we already mentioned that Schrödinger equations is a kind of an eigenvalue problems. So once we have this matrix, we are able to solve or to find out those wave functions with corresponding eigenenergy EI. And these wave functions, okay, denoted as I1, 2, 3. These wave functions actually they forms a complete orthogonal set, which means that phi I complex conjugate phi j, okay, equals to delta ij. That has only two values. When I equals to j, it equals to 1. Okay, so this is pretty straightforward. Phi 1 and phi 1, of course, that is 1, because we find the probability of this phi 1 in this space is 1. But if you want to overlap integral with from phi 1 to phi 2, because this system, this quantum number is not the same, okay, then it equals to 0. Okay, so we can say that phi I and phi j actually equals to delta ij. Okay, this delta functions is Kronecker delta functions. Only when I equals to j, we have values 1. Otherwise, it equals to 0. So this is the orthogonality. And this is a very important concept, which means that each wave functions, they are all orthogonal. Okay, each wave functions, they are all orthogonal with each other, and that will give us a very useful and important relationship when we try to derive other advanced and complicated problems in the future. And then comes the expectation values. Okay, so define the position R of phi state, because this R is an observable parameters. Okay, so what exactly is R for phi state? So we can write this bracket R as an expectation values. Okay, so how do we write down these expectation values? We use this probability density to multiply with this R, and integrate over the space. Okay, and that will give us the expectation values of this R. And because this probability density can be expressed as phi complex conjugate times phi, okay, or this phi squared times R, okay, and since we can express this as this one using the direct notations, can be this bracket phi times R acting on phi. Okay, so R now becomes an operator acting on phi and then multiply with the complex conjugate phi complex conjugate and integrate over the space. Okay, so you can use the same concept to obtain the energy or average energy of this state or average momentum of these states. So what is the average energy of this phi state? You use this bracket E equals to phi star because we know that E is an operator. This operator is JH bar d phi over dt. Okay, d phi over dt. And P is also an operator. That is minus JH bar gradient. Okay, great. Gradient. Yes, gradient phi, and multiply with phi complex conjugate and integrate over the space. Okay, integrate over the space. We can also know that from the Schrödinger equations, H acting on phi I will give us the eigenvalues EI. Okay, because EI only belongs to this phi I. So if we multiply a complex conjugate and integrate over the space, okay, these Schrödinger equations now become this one and this one. Because EI is only a value, okay, is only a value. So it's not an operator anymore right now because this EI is an eigenvalue. So we move this out. So this one equals to 1. So this one actually is the expectation values of the Hamiltonian. Therefore, expectation values of Hamiltonian actually is the energy itself. Okay, so it returns to the classical physics right now. Okay, I'll stop here and will give you the examples in the following lecture. So see you later. Bye bye.